transformation temperature materials, which usually have not really an exact official definition or a thing you can point to, but they have some things in common, and I'm going to explain those things. One of the things they have in common is a relatively low martensite start temperature. And having a look on the schematic diagram on the right, we in this first thing see how a normal filler behavior would behave. Starting from relatively high temperatures, we have a bit of shrinkage. Then we have the phase transformation at fairly high temperatures, which leads to compressive stresses. Well, here you see stresses due to shrinkage and due to phase transformation. And then after the phase transformation, we still have a lot of shrinkage, resulting in comparatively high residual stresses for welded joints. When we use LTT filler materials, we first have a lot of shrinkage to comparatively low temperatures. Then we have the phase transformation, and now the phase transformation is able to induce more compressive residual stresses, as the yield strength at this temperature is much higher than at the higher temperatures for the normal filler material. And after the phase transformation, we have a bit of shrinkage, but in the end, our welded joint has more or less low tensile or compressive residual stresses. This is the reason why people use and want to use those filler materials. Another thing they have in common is relatively high alloying element content. They can have up to 15 weight% of nickel and 15 weight% of chromium. And it is usually suggested to use them for higher strength steel, so with a yield strength of at least 690 MPa. This is an example of how they work in practice. You can see here X-ray measurements of residual stresses in such a longitudinal stiffener. And the longitudinal stiffener was welded in two ways. It was first normally welded, and then we made two passes around the ends of the stiffener, where we would usually expect our fatigue crack to start. And an additional normal filler material leads to tensile residual stresses in the notch where the crack would start. And if we do those two additional passes with LTT filler material, we can induce compressive residual stresses. And the effect of that can be seen in the fatigue strength too. These are fatigue tests. The black ones are the film or the longitudinal stiffener welded with normal filler material, and if we use that LTT filler material, we can see the fatigue strength goes a bit up. So we have seen that those filler material can lead to beneficial residual stress state and higher fatigue strength. So they are suggested to be used in welded structures. But there are indicators that they can have a relatively low toughness temperature, and that it might not be sufficient for example, structural applications. One literature, for example, reported between 20 and 35 Char-PV joule impact energy at 20 degrees Celsius, which is relatively low. So we thought that we would determine the toughness of LTT filler material with basically two tests. One was Char-PV impact energy temperature to transition curve, and the other test were fracture mechanics tests at different temperature levels. As a base material, we used the S690QL, and as a filler material, we used a filler material which can be bought, and it is supposed to be a soft martensitic stainless steel, which is usually used, for example, for the repair weld of turbine shrouds. Here on the right-hand side, you see the chemical composition of the filler material, which has around 12% of chromium, 4.5% of nickel. And we use this filler material because it has been used in other research projects before, and we saw that it led to a beneficial residual stress state. So when buying this material, there are recommendations how to deal with this material. For example, they suggest to use a preheating temperature and an interpass temperature of 100 degrees and up to 180 degrees Celsius, and to have a post-weld heat treatment of 600 degrees for 8 hours. When it is used as LTT filler material, usually lower preheating and interpass temperatures are used, and there's no post-weld heat treatment done because it would be similar to a stress relief treatment, and we want those beneficial compressive stresses. We used metal active gas welding with a shielding gas M21 and preheating and interpass temperatures of 50 degrees Celsius. We aimed at 5 times between 5 and 15 seconds and measured times between 6 and 13.5 seconds. We used 2 weld preparations. One is the double V groove to be able to induce a notch within the weld seam, and the other one was a single V groove to be able to induce a notch within the heat affected zone. Here are macro sections and hardness measurements of our materials and of the joints we made. We see that we have relatively high hardnesses for welds made in structural steels, up to 450 vicas within the weld seam. And for the single V-notch groove, it was comparatively difficult to weld with that material, and the way LTT filler materials are usually welded. So when we put a notch in the heat affected zone, but partly this notch goes through the weld metal as well. For the impact toughness tests, we did tests between -115 and 80 degrees Celsius. On the left-hand side, we see the double V groove. We see it has a comparatively low upper shelf of below 50 joule and a relatively long transition range. On the right-hand side, we see the samples that were notched in the heat affected zone with a much higher upper shelf and a lower transition temperature as well. We found a transition temperature of -50 degrees at 28 joule, and for the notch in the weld metal, we found a transition temperature of -42. This was the reason why we did our fracture mechanics tests with the samples that were notched within the weld seam. These are the results of our fracture mechanics tests. We did tests according to the ASTM E1820 with SCB specimen of 9 times 18 millimeters, and of course thickness corrected our results. We see a temperature dependence of the fracture toughness. So at lower temperatures we are in a range between 35 and 60 megapascal square root meter, and coming to temperatures around -20 and -10 degrees, we tend to go up to toughnesses between 73 and 82 megapascal square root meters. We had 2 more specimens which failed in a ductile manner, so they aren't included in the KJC results. One was tested at -10 degrees and one was tested at room temperature. And after testing, we made macro sections to ensure that the notch stayed within the weld seam and we had no crack path deviation. So these are basically our results. I'm going to discuss them and sum them up. We used LTT filler materials which we welded and characterized. We would suggest to have a more official definition because there's really a broad range of chemical compositions that are supposed to be LTT filler materials. Here we used film material that was used in earlier research with 2.4% of chromium and roughly 4% of nickel. When welding those film materials, it is suggested to use relatively low preheating temperatures to produce short heat at 5 times, and we saw during welding that this can lead to an increased porosity, and we'll have a look on that in future research. Which is mainly due to the fact that the welding parameters differ significantly from the recommendations of the producer of that film material. We saw that the impact toughness and the fracture toughness could be sufficient depending on the design temperature and where, in which circumstances you would want to use it. But we recommend to do toughness testing when those materials are suggested to be used in future research or even in practical applications. So with this, I want to thank you for your attention, and I'm open to questions.